Hey folks, today we're going to talk about the inverse Z transform. There are actually three different ways of doing the inverse Z transform, and I have them written in. They're in the write-up. So if you want to take a look at that, all three of them are reasonably easy, but I'm going to pick the easiest one, and that's what I'm going to show you. So let's begin. So the formal definition, and that's one of the ways to do it, is that x of n is equal to 1 over 2 pi j, the contour integral, and the contour goes this way, of x of z to the n minus 1 dz. Now, initially this looks kind of messy, but it really isn't, because all you have to do is find the residues of the poles that lie inside of the contour. The contour, by the way, has to go through the region of convergence. And so then if you find all of the poles inside of the region of convergence, then you can find the residues of those poles and add them together, and you get the inverse Z transform, and that's one way to do it. And the residues are kind of the way you would do a partial fraction expansion. So anyway, but that's the formal definition of it. And I have a brief description in the write-ups, and so you can take a look at that. The easy way to do it, I think, is to use the method that we used in the case of the Laplace transform. We have a couple of template Z transforms, so we know that the Z transform of a to the n u of n is equal to 1 over 1 minus a z to the minus 1, or z over z minus a, the region of convergence being z greater than a, because it's a right-sided sequence. Or we have the Z transform of a to the n u of minus n minus 1, and that's equal to minus z over z minus a. And the region of convergence, of course, because this is a left-sided sequence, the region of convergence is z less than actually the magnitude of a. So those are our template functions. So what we can do is we can take whatever x of z is, and we can write it in these terms. So what we'd like to do is we'd like to take x of z and write it as this. Some coefficients times z over z minus whatever the poles are, minus p sub I. Or we can have this as p sub I squared, because remember, if I took the derivative of this, if I multiplied this with n, that would be the same thing as taking minus z times the derivative of this, and I would get something like, I think it was az over z minus a squared. If my region of convergence z is greater than a, then the corresponding discrete time function is just n times a to the n u of n, right? So as long as the denominators here are either z minus pi or z minus pi squared or cubed or something like that, I can always find the inverse Z transform by going to my template functions. Okay, so this is what I want to do. But I do have a way of expanding x of z. And for the moment, I'm just going to take the case where we have simple poles, and that's pretty much where we're going to stick with. But remember that if you didn't have simple poles, if you had higher order poles, you could find the inverse Z transform of those as well. But for the moment, let's just stick with simple poles. So this is what I would like to have. What I actually do have for the case of the simple poles is I have something like this, where I can take x of z and use partial fraction expansion, and I can write this instead of a sub I, let me use a different letter, so let's call it b sub I over z minus p sub I. This I know how to do. This is just partial fraction expansion. But this is not what I want. What I want is something which is z over z minus the poles. And I can do that really easily, because all I have to do is divide both sides of this with z. So now I have x of z divided by z. And that's just, I can now use my partial fraction expansion skills, and I can expand this as a sub I over z minus p sub I. And then once I have found what these a sub i's are, then I just multiply it through, and that means that x of z can now be written as, once I've found the a sub i's, can be written as summation a sub I z over z minus p sub I. So that's the whole trick. Take your x of z, whatever it is that you want to find the inverse z transform of, divide it by z, and then use the partial fraction expansion to write it in this form, and then just multiply it through by z on both sides, and now you'll have terms of this kind. And by looking at the region of convergence, it'll be either this kind of a term, that'll be the inverse z transform of that, or it'll be this kind of a term. So if the region of convergence for a particular term, say for P1, is that magnitude of z is greater than P1, corresponding to that, I get an inverse z transform, which is A1 times a to the n, or P1 to the n u of n. If I have, say, the next one, z minus P2, and the region of convergence is something which is less than P2, then I would just use this template. Okay, so let's do an example and kind of beat it to death. So the example that I'm going to use is this. So I have x of z is equal to this odd looking one, but 48z squared minus 16z over 8z squared minus 6z plus 1. And the region of convergence is z greater than a half. Okay, so that's my region of convergence. Now, what I need to do now is write this, find the poles, and then write this as a product of terms of this kind, and then just do the partial fraction expansion. Before I do that, because this one will just be some z minus, and I've got z squared, so there'll be two poles. So z minus p1 times z minus p2, I'm going to get rid of this 8 by dividing top and bottom by 8. So this becomes 6z squared minus 2z over z squared minus 6 over 8 is 3 over 4 z plus 1 over 8, right? And now I can find the roots of this polynomial, and so z12, or I suppose p is what I'm using, so p12 is equal to 3 over 4 plus minus square root of 3 over 4 squared, so that's 9 over 16, minus 4 times 1 over 8, so that's a half, divided by 2, or that's equal to 3 over 4 plus minus square root 9 over 16, and I can write 1/2 as 8 over 16 divided by 2. So 9 over 16 minus 8 over 16 is 1 over 16. The square root of 1 over 16 is 1 over 4, so this becomes 3/4 plus minus 1/4 over 2. If I take the plus, 3/4 plus 1/4 is 1, so I get 1/2. If I take the minus, 3/4 minus 1/4 is 1/2. Divided by 2 is 1/4. So my poles are at 1/2 and 1/4. Okay, so now I have x of z is equal to, I divide through, so this was 6z squared minus 2z divided by z minus 1/2, z minus 1/4. Okay, so let me go to a new page, and I'll just copy this down. So x of z is equal to 6z squared minus 2z over z minus a half z minus a fourth, right? And magnitude of z greater than a half is my region of convergence. Okay, now what I'm going to do now, I want to expand this using partial fraction expansion, but I don't want to expand x of z. I want to expand x of z divided by z. So let's divide both sides by z. It's equal to, if I divide the numerator by z, I'll get 6z minus 2 over z minus a half and z minus a fourth. Okay, so now I can write this as a over z minus a half plus b over z minus a fourth. To find a then is equal to 6z minus 2 over z minus a fourth, evaluated at z equals 1/2. Plugging 1/2 in here, 6 times 1/2 is 3. So I've got 3 minus 2 over, and plugging in 1/2 here, I have 1/2 minus a fourth. Right? So 3 minus 2 is 1. 1/2 minus a fourth is a fourth. So that's equal to 4. A is equal to 4. B is equal to 6z minus 2 divided by z minus a half. And I have to put z equals 1/4, evaluated as z equals 1/4. So 6 times 1/4, 6 over 4 or 3 over 2, minus 2 over a quarter minus a half. So this is going to be 1.5 minus 2 is minus a half. And a quarter minus a half is minus a quarter. So that's equal to 2. Okay, so x of z over z is equal to 4 over z minus a half plus 2 over z minus a fourth, right? And the region of convergence, z is greater than a half. And you kind of got an indication that z equals 1/2 was the pole because of the region of convergence, but we'll kind of ignore that. So now I know what, so now what I do is I multiply it through by z, so I get x of z is equal to 4 times z over z minus a half plus 2 times z over z minus a fourth, and z is greater than a half. Okay. This thing here, the inverse z transform of z over z minus a half, is just for a region of convergence that is outside of a circle, is just 4 times 1/2 to the n u of n plus, and in this case, z over z minus a fourth. Again, the region of convergence is outside of a circle, so that's just 1/4 to the n u of n. And this linearity of the z transform, let's just put that 2 over here, and that's it. So x of n is equal to this. That's it. That's all the inverse z transform that you need. Okay? And this will work for most of the stuff that we do. For everything that we do, but for most of the problems that you'll see. Sometimes, like I said, you might have higher order poles. And if you have higher order poles, then again, you can do the partial fraction expansion exactly the same way. But the higher order poles will then, the template that you'll use won't be x of n, or 1/2 to the n u of n, but it'll be n times 1/2 to the n u of n, right? Instead of a to the n u of n, you'll have n times a to the n u of n, or n squared times a to the n u of n, depending on what the order of this pole is. But we will stick with simple poles, so I'll just leave that for whenever you're faced with that problem. Just remember it. Okay, so that's what we did if z was greater than a half. Let's do the same thing. Let's take the same problem again, but this time let's just change the region of convergence. So we'll take x of z to be what we had before, 6z squared, and I'll write this like this, 2z over z minus a half, z minus a fourth. But let's say my region of convergence was magnitude of z greater than a fourth and less than a half. Right? So again, we go through the whole thing and we end up, so up to here, nothing changes, right? We just write x of z in this form. And then when we do the inverse z transform, then something changes. So I can write x of z as what was it? 4 times z over z minus 1/2 plus 2 times z over z minus 1/4. Right? So let's take a look at each of these individual terms and expand them according to the region of convergence. So in this case, the first term here has a region of convergence that is inside of a circle. Right? Because it has a region of convergence that is inside of a circle, this will be a left-sided sequence. And so I'll get x of n, as far as this term is concerned, is going to be minus 4 1/2 to the n u of minus n minus 1. And then as far as this term is concerned, z minus 1/4, the pole is at 1/4. And the region of convergence is outside of that pole, and therefore this won't change. It'll be the same as before, and that's just be like that. Okay, so that's it. It is really as simple as that. Take x of z, instead of taking x of z and writing the partial fraction expansion, takes x of z over z, and that's an important step, and then write the partial fraction expansion. And once you've got that, then multiply it through by z, so you get terms like this. And I know what these are the z transform of. Anytime I have z over z minus a, I know that is the z transform of either a to the n u of n or minus a to the n u of minus n minus 1. Right? So once I have this, I got everything. Okay, so this is the method that we will use. Okay, there is another method. And let me show you that just because it's kind of an interesting method. So here's the idea. X of z is equal to summation n equals minus infinity to infinity x of n z to the minus n. Right? So let's take the case of a right-sided sequence. So we have an x of z which converges outside of a circle. It's a right-sided sequence. If it's a right-sided sequence, then this will be, so for a right-sided sequence, x of z is equal to, all the x of n's for n equal n less than 0 are 0, so this becomes n equals 0 to infinity x of n z to the minus n, right? Or I could write it out as a polynomial of z to the minus 1. So this will be x of 0 times z to the power 0 plus x of 1 times z to the power minus 1 plus x of 2 times z to the power minus 2, etc., etc., etc. Okay? So if you give me x of z, and I can write it in this form, then by just looking at the coefficients of this polynomial in z to the minus 2, I can find what the values of x0, x1, x2 are, And if there is some regularity in these, I can find out what the general expression is. Okay, so like I said, I mean, this is a kind of a curious thing. So let's just do it. So let's take the example that we had. If I can find it, it was x of z is equal to 48z squared minus 16z over 8z squared minus 6z plus 1. And the region of convergence was, let's use this region of convergence. So it's a right-sided sequence, so it fits in with our example here. Now, to do this, all you have to do is just do long division. And everybody learns long division in a slightly different way about how to write it. This is the way I learned it, so that's the way I'll write it. So this is 48z squared minus 16z. So that's this part. And then there's the divisor is here. So this is 8z squared minus 6z plus 1. Right? So now I have, if I do the division, 8 times, I'll get 8 times 6 is 48. So I'll get 6. That'll give me 48z squared minus 6 times 6 is 36 minus 36z plus 6. That gives me 0 here, minus 16 plus 36 gives me 20z, and 0 minus 6 gives me minus 6. So now the next term is 8 goes into 20 how many times? Well, 2.5 times, right? So it'll be plus 2.5. And I need a z here. I have a z squared here. So this has to be z to the minus 1. So that'll give me 20z. And then minus 6, 12, 3, 15. So minus 15. And this is z times z to the minus 1. Cancel each other out. And then plus 2.5 z to the minus 1. Right. So now that gives me minus 6 plus 15 is 9. And then minus 2.5 z to the minus 1. And then the next term will then be, I need to get 9 here. I have 8z squared. So this will be plus 9 over 8 z to the minus 2. And that'll give me 9. And then etc., etc., etc. But you can see how this is going. It's going, the first x of 0 will be 6, x of 1 will be 2.5, x of 2 will be 9 over 8, etc., etc., etc. Is that really what we got? Well, if you go back to what we had, we'd found that x of n was equal to 4 times 1/2 to the n, u of n, plus 2 times 1/4 to the n, u of n. Right? So x of 0 would be 4 times 1/2 to the power 0, that's 4, plus 2 times 1/4 to the power 0 is 2, so that's 6, which is what we have. And then x of 1 is equal to 4 times 1/2 to the 1, plus 2 times 1/4 to the 1. And so that gives me 2 from here and 1/2 from here. So that's equal to 2.5, which is what we have here. Okay, and then x of 2, if I did my division right, is 4 times 1/2 to the power 2, or 1/4, plus 2 times 1/4 to the power 2 is 1/16. And so that is 1 plus 2/16 is 1/8, which is equal to 9 over 8, which is what we have here. Okay, so if I have a right-sided sequence, what I do is I go through and divide it in this form, and the quotient here gives me x of n. If I have a left-sided sequence, then what I need to do is flip this. So instead of writing this as 8z squared minus 6z plus 1, if I flipped it and wrote it as 1 minus 6z plus 8z squared, what I would get would be the left-sided. So if this hadn't been z greater than a half, if it had been magnitude of z less than a quarter, then I could have flipped this, and I would end up with a polynomial in, instead of a polynomial in z to the minus 1, I would get a polynomial in z, and that would be the thing going the other direction, and we'd get a left-sided sequence out of that. But, you know, you don't have to know it. Just, this is more for curiosity. So actually there are 3 different ways, and I'm going to hold you responsible for only one of them, and that's this one. That given an x of z, take that, divide it by z, write it as a partial fraction expansion, and you'll have some region of convergence, and then x of z then can be written as summation a sub I z over z minus I, z sub I, and with the same region of convergence. And now you take each term separately, individually, and according to the region of convergence, look at which of the two template sequences correspond to that. And if you do that, you can add all of them together, and you'll end up with x of n. So in the end, you'll get x of n is equal to, let's assume that the region of convergence is outside of all of the poles, then this would become a sub I z to I to the n u of n. Right? It'll be that simple. That's it. Okay, guys. So that was the inverse Z transform. Like I said, there are 2 other ways, and I have those written in the write-up. So if you're interested, go look at them. They're interesting. They're not that difficult, but this one is the easiest one. So this is the one I end up using pretty much every time. Okay. I'll see you